Good morning, UCF! If you get that reference, then I'm proud of you because it's pretty old. Today we're going to be talking about crystalline solids, coming straight to you from my freezing cold office. We're going to look at things like ionic solids, like these beautiful sodium thiocyanate crystals. And you'll notice my very pretty nails that my youngest daughter painted. Don't be jelly. We're going to look at network covalent solids, like this glass with this pretty image of Taj Mahal in the middle of it. Things like buckyballs right here, multiple carbon atoms bonded together. We're going to look at metallic solids, like this copper sheet. So fancy. So let's get into our PowerPoint slides here. So classifying crystalline solids. You've learned about intermolecular forces. You learned about lattice cells. So you know how those crystalline solids come together. So we're going to look at what are the different types of crystalline solids, what are those components that make up all those points in the lattice cell, the corners, the faces, the body centered, etc. And how are they different? How do we categorize them? So we've got our three main categories: molecular, ionic, and atomic, and then these three subcategories under atomic. So again, these are the composite units of this crystalline solid. If we had a basic cubic lattice, what types of things are we going to see in the corners? Are we going to see molecules or ions or individual atoms? And of course, there's different types of atoms. We have metals, metalloids, non-metals, and how does that affect certain properties within those categories? What can we assume? That one type of category crystalline solid is going to have a low melting point, or other categories are going to have higher melting points. So we're going to start with the molecular solids. So again, our lattice sites are occupied by molecules, all kinds of different molecules. Could be carbon dioxide, could be water, could be sugar, whatever. So if we have an entire water molecule in one corner and another water molecule in the other, what's the attractive force between them? It's only those intermolecular attractive forces, not the actual bonds or intramolecular attractive forces. So because of that, these are going to be relatively weak. We're going to have relatively low melting points in our molecular solids. And what we're going to see also in crystalline solids is we can actually have lots of different crystal structures in the same type of material. So some you may not be aware of. We'll look at water, chocolate, and a couple of other things. Those are called polymorphs. So here's an example of molecular solids, and this is from the publisher. I forgot to change the picture. You'll notice that the toluene here is identical to the benzene, but of course in reality they aren't. They have different structures. This should have an extra carbon atom. But what you can see is these are affected, or only have one type of intermolecular force, London dispersion forces, and they have relatively low melting points in these instances. This is an example of that polymorphism we talked about, those different crystal structures present within the same type of molecular crystal. So for chocolate, you may have, if you've been watching all those fancy baking shows that occur now, notice they talk about tempering chocolate. So what they're actually doing here is heating the chocolate in a certain way and controlling how they heat it or how they cool it to get a different crystal structure. And those different crystal structures are going to have different textures. They're going to have different melting points. So if you want a chocolate that doesn't melt as easily, or that isn't as grainy, has a more smooth taste, whatever, that's what they're doing there, and that's what those different crystal structures are and how they affect it. Same thing with water. You think of water. If I told you you had an ice cube and you put it in a glass of water, what's it going to do? It's going to float, and it's always going to float, and that's what you're used to. Well, the reality is there's actually several different crystal structures of water. So if we look at a phase diagram here for water, what we would normally expect is there's our pressure, here's our temperature, and here is our line between liquid and gas, and here's our solid right here. So solid, liquid. That slope of that line in between the two is actually a negative slope. That indicates that the density of the solid is less than that of the liquid. Well, the reality is there's multiple crystal structures of water. If we start to increase the pressure a lot, or we get to really, really, really cold temperatures, what we'll see actually is a positive slope. And within there, we may have all kinds of different crystal structures. So the one you're used to for water is crystal structure 1, which is less dense than liquid water. But we also have a crystal structure 2 and a crystal structure 3. And I think there's 5 different crystal structures of water. And some of those are actually more dense than liquid water. So if you had those crystal structures of water, you had that type of ice, you would put it in a glass of water, and instead of seeing it float, it would actually sink. So that's what the polymorphism of those different crystal structures are, and that's kind of why they're important. Is sometimes they're simple cubics, sometimes they're octahedral crystal structures, sometimes they're rhomboid or something else, and that's going to give it slightly different properties in those instances. All right, so those are our molecular crystal structures. Next is ionic. So just like it sounds, ionics, the lattice sites are occupied by ions, so positively charged cations or negatively charged anions. So these are much stronger attractive forces because we're looking at a complete total negative charge or positive charge, and that electrostatic interaction is much greater. So ionic solids are going to have very high melting points. And then when you think about that crystal structure, where are those ions going to take place? Within that crystal lattice, you're going to have some points occupied by the positively charged ion and other points occupied by the negatively charged ions. And these all going to have, just like we saw before, different coordination numbers, different ways that they orient within that crystal lattice. Sometimes in this case, the positive ion is body centered and we have all those negative ions in the corners. And of course, this is just a single unit cell. So we're going to see this repeating throughout. And we're going to see then that we get a certain formula unit for this, a certain ratio of cesiums to chlorides and how they orient in space. So this is one structure, the cesium chloride structure. Your book has a whole bunch of other ones, rock salt with octahedral holes and how that's going to look. This is what sodium chloride does. You have fluoride structures. We're not going to worry about these specific structures. We're not going to quiz you on a rock salt structure or a fluoride structure. Just know what an ionic crystalline solid is. How do you identify it? Is that typically going to have strong attractive forces or not? Is it going to have a high melting point or not? You can go through these for fun if you want. These are in the slides or in your textbook. You can kind of see some very specific examples of different types of ionic crystalline solids and how they align in space. But again, nothing we're going to test you on. Next are our atomic solids, of which we have three kinds. We have non-bonding atomic solids. So again, the composites that make up the unit cell or the crystal lattice are going to be individual atoms. And in this case, they're non-bonding. So usually what this good example would be noble gases. So they're not diatomic, they're not polyatomic like oxygen, where we actually have an oxygen atom and an oxygen atom, and they're covalently bonded to each other. Here we have a xenon and a xenon in the crystal structure. And where's my other hand? Oh, there it is. And the only attraction they have are dispersion forces. They don't have an actual bond. They only have intermolecular attractive forces, which are pretty weak. So non-bonding atomic solids are going to have very low melting points, which makes sense, right? If we want to turn a noble gas into a solid, we're going to have to get it really, 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 really cold. Next is metallic atomic solids. So looking at these, any kind of metal from lithium to titanium to lead is going to have this. We know that metals have access to that D subshell, and the D subshells are actually relatively close in energy to the S subshell. So 4s is relatively close in energy to a 3d. What that means is those electrons can very easily travel between those energy levels. If we don't have a full D subshell, we can easily start to move maybe some electrons from the S subshell to the D subshell and populate it. So what that gives us is what we call a sea of electrons. So we have our population of metal atoms. So let's say we have a bunch of lead atoms or copper atoms like you just saw there. Here's my nuclei. So all those trillions upon trillions of copper nuclei. And there's their electrons orbiting that nucleus. Well, they can actually very easily, because they can transition to different energy levels, they can easily sort of move around here. And what we get is this constant sea of electrons, or these negative charges spread throughout, giving us these electrostatic attractions between all these electrons and positively charged nuclei. This is why metals are so malleable and ductile. This is why it's very easy to draw them out into a sheet like this. That's why they're extremely good conductors of heat and electricity, is because of that sea of electrons. And this makes for some pretty strong bonding as well. So we're usually going to see very high melting points in metallic crystalline solids. Some examples, different ways that those atoms can stack, and how we're going to see that, how that's visually going to be represented in a larger macroscopic sample. So conceptual question, which solid would you expect to have the highest melting point? So we've got to look at all three of these and identify what they are. Here we've got magnesium oxide. So I've got a metal and I've got a non-metal. What is that? Ionic. So we've got an ionic crystalline solid. I've got iodine. What's iodine? It's a non-metal, but it's I2, it's diatomic, so it's an iodine that's actually bonded to another iodine. That is a covalent crystalline, atomic crystalline solid. And then we have krypton, that is a noble gas all by itself, so it's not actually bonded to anything. So that would be a non-bonding atomic, so very low melting point. So out of all of these, that ionic solid should have the highest melting point. So and last then is the network covalent atomic solids. So again, single atom, usually single type of atom. We'll see later, there can be others. But in this case, they're actually covalently bonded to each other. So very strong. So for carbon, the most common ones you've probably seen or you've at least seen pictures of, are graphite and diamond. In graphite, we have sp2 or sp squared hybridization. So what this does is creates a trigonal planar geometry. So you can see with graphite is we have covalent bonds across that horizontal plane with that trigonal planar geometry. So within that horizontal plane, extremely strong attractive forces. But between the planes, the only thing that we have instead of those actual covalent bonds is the dispersion forces, or those intermolecular attractive forces, which are much weak. This allows those planes to easily move past each other. So that's why graphite has that slippery feel. That's why it's a much more brittle solid. But those planes themselves are covalently bonded. They're still very strong. It still has a very high melting point. This is a good insulator, very non-reactive. Because of those planes can glide, this makes a good lubricant. That's why you'll see things like graphite spray. Diamond, similar. Covalent bonds made out only of carbon, but now we have sp3 or sp cubed hybridization. So this gives us a tetrahedral geometry. So we can see here, not only do we have actual covalent bonds in the horizontal plane, but also in the vertical plane. So this is much more rigid, much stronger than graphite. Those planes aren't easily going to be able to move past each other. That's going to alter some of its other properties based on that. High pressure favors the formation of diamond from graphite. What can you conclude about the densities of the two substances? Diamond is more dense than graphite. Graphite is more dense than diamond. Nothing can be determined about the relative density. So all this information is extraneous to that. Well, if high pressure favors it, then it should be more dense. We should see a positive slope in our phase diagram of this. We need more pressure, meaning those molecules are closer or tighter packed in the diamond, so that we can conclude it's more dense than graphite. Other examples, buckyballs, Buckminster fullerene. We found out there's all kinds of different ways that carbon can bond, not just like it does in graphite and diamond. So we can make these ball structures like this, known as buckyballs. We can make nanotubes, nano walls, all kinds of different things. And these also have differing properties. Sometimes they're good for putting a different molecule inside of this and introducing it into a new sample. Or we'll get things with extremely high tensile strength, or things where we can control the conductivity. You're not gonna have to know these specifics. It's just something to relate it to the real world and all the different uses here. Silicates, silicon oxide, glass, you've seen that before, still network covalent. Now we have two types of atoms, but they're covalently bonded and they're creating the specific crystalline structure here. Ceramics, again, you don't have to know any of these are just specific examples. What are the different crystal structures we get as we introduce other atoms? How does that affect the properties? Ceramics, of course, are very handy dandy. We like those because we can control them. They're relatively easy to make. We can get different shapes and different properties out of them and use them in all kinds of different types of industries or walks of life. Another example of this, steel. You may not know it. Steel is actually a ceramic. It's not just iron, it's a combination of iron and carbon. And the way that those carbons align within that iron and the different crystal structures it gives us different properties. So just like we saw with the chocolate and the water, we have different crystal structures for steel. This comes into play when you're making tools, or a long time ago when people were making swords. So with this sword here, you'll notice that line, that differential color. This actually has different tempers. These are different crystal structures. So the crystal structure on the edge here might be slightly different than on the back end. This might be a crystal structure where this more easily takes an edge, and here this might be something that's more durable or elastic or something like that. So that's another example of different tempering and getting different crystal structures within that. Other examples of ceramics, cement, glass, you guys can go through those yourselves. They're just there to give you some more real world examples if you want, if you find it interesting. We're not going to quiz you on any of these specific things. Like I said, this is more just if you find this fun, you want to know a little bit more about it. The main takeaway here just comes back to this. Do you know what those different types of crystalline solids are? Can you identify them and categorize them? If we gave you 3 and we said, which one of these is the ionic solid? Could you tell us? Or if we gave you 3 different samples and said, which one's going to have the lowest melting point? Could you put them into the different categories and say, oh, that one's going to have the lowest melting point because it's a non-bonding atomic solid, or whatever it happens to be. So that's the end of this video for me. Again, I hope you found this helpful. Any feedback's much appreciated. Let me know what we can do to make these videos better, more accessible. And we'll see you around again. Peace.